Hi, welcome to MA212. Sorry I couldn't make the class today. Let's go ahead and talk about what we were going to talk about. I'll do it sort of briefly. That's modeling using systems of differential equations. Now, last time we were talking about predator-prey systems here in section 1. And we said, let's imagine that we have two species. We'll call one species X and one species Y, and that species X preys on species Y. So population X is the predators, population Y, that's the prey. In the end, what we're always going to come down to is saying that the rate of change in any population is the birth rate here minus the death rate. It doesn't matter if that's for the predator or the prey, or if we're talking about a logistic equation, or if we're talking about a competition model. That's what it comes down to. Rate of change, birth rate minus death rate. Okay, this should remind you of when we did salt tank problems, when we said the rate of change of salt, well, that's the rate of salt coming in minus the rate of salt coming out. Same exact kind of thing here. The question is, how do we quantify the birth rate and the death rate? With this kind of modeling, we just have to make some assumptions. So the assumptions that we're making in this classic predator-prey model is that the birth rate of the prey at time t is just proportional to its population. So if there's a lot of prey running around at time t, then the birth rate is high. And if there's not many prey at time t, then, well, they're not reproducing very quickly, right? So we're just going to say proportional to the population, so it's some constant, we don't know what constant, times the current population. Now the predators, on the other hand, we are assuming that they need prey present in order to reproduce. Maybe they have to feed their young or something. Okay? So what we're saying is that if the current population of predators is low, well, then they can't reproduce very quickly. And even if there are a lot of predators present, if there's not much prey present, then the predators can't reproduce quickly. What we're assuming is that the birth rate of predators at time t is jointly proportional to x and y. So that means it's proportional to the product of x and y. So that's how we're going to model the birth rate of predators at time t. Now, the death rate of predators at time t, we're assuming that that just depends on the current population at time t. So if you have a bunch of predators running around at time t, presumably some of them are old and they're going to die. And if there's not many predators running around at time t, then there's not many old ones, so you don't have a big death rate. Okay? So death rate of predators is just proportional to the current population of predators. And the death rate of prey at time t, again, if there's a lot of prey running around and no predators, then the prey don't die very fast. If there's lots of predators but no prey running around, well, they can't die very fast if there's not very many of them. But if there's a lot of both, then the predators eat the prey very quickly and there's a high death rate. All right? So we're going to assume that the death rate of prey at time t is jointly proportional to x and y. We're assuming that there's no migration, so the population of each species only changes through birth or death. Okay? So the rate of change in the population of the predators, well, that's going to be the birth rate of the predators minus the death rate of the predators. And the rate of change of the population of the prey, that's going to be the birth rate of the prey minus the death rate of the prey. We'll just plug in our assumptions, and we get this system of differential equations. This is very famous. This is a Lotka-Volterra predator-prey system. And you'll see it in many books. Now, what should you be able to do with this system of equations? One, you need to be able to find the equilibrium solutions. Second, if I give you numbers for A, B, C, and D, you need to tell me if those equilibrium solutions are stable or unstable. Okay, and that's what you're going to need to do throughout this. Let's talk about another kind of equation, the logistic equation. This is a model for just one single species. It's just the population of a single species, but it's instructive to talk about this before we talk about competition models. So let's just let x of t be the population of some species. Maybe it's rabbits out in the woods. I don't know. And you'll notice that the woods, they can't handle just an infinite number of rabbits, right? Let's just suppose that our environment has a particular carrying capacity k. What that means is that the environment can only support k members of the population. If the population gets above k, then your population should start declining. Okay, that's what we're going to assume. Again, there are lots of ways we can do this. I'm only going to investigate one very classic option. All right. Let's assume that the birth rate of the current of the population is just proportional to how many members of the population there are, just like we did last time. So we'll assume that the birth rate at time t is some constant r times the current population x. Okay. Now, we haven't taken the carrying capacity into account at all. What we want to do here is let's make the death rate variable with the current population, okay? What we're going to do is this. We're going to say the death rate is proportional to the current population, but that the constant of proportionality varies with x. So what this means is that maybe if the population is down near 0, then the proportion c that die at any time is not very big. It's near 0. But as the population gets up towards the carrying capacity, then the proportion of the members of the population that are going to die gets bigger, okay? The closer the population gets to the carrying capacity, then the higher that percentage of the population that die is going to be. Okay, now, what's the carrying capacity in particular have to do with this? Let's work it out so that once you get to the carrying capacity here, that the proportion of the population that's going to die matches exactly sort of the birth constant of proportionality, okay? And that once you get above the carrying capacity, then the proportion of the population that's dying is higher than the constant of proportionality for the birth rate, okay? So that means that once your population gets up above the carrying capacity, you have members dying faster than you're reproducing. Okay, so that should lead to population decline, which is what we want. That's an accurate reflection of things. Okay. Okay, so let's make this constant of proportionality. Again, what we want is when the population gets above k, then this constant of proportionality gets above r. R is the constant of proportionality for reproduction. So we're just going to make the constant of proportionality for death. We'll make it be x over k times r, which makes the death rate altogether, right? This is the portion of your population that's dying. So you multiply it by the total size of the population to get the actual rate. All right. And that's your death rate. So it's rx over k times x, okay? So we'll go ahead and put this all together. Again, the rate of change in our population is the birth rate, Rx, minus our death rate, right here. And if you look in the book, you'll see the logistic equation expressed in these terms, this last equality, which is fine. I prefer to think of it as in minus out, but they like to factor things out. So that's fine. Okay, that's the logistic equation. Now let's talk about the very last model on the docket, the Volterra competition model. So a competition model describes the populations of two species that are competing for a shared resource. So maybe you have, I don't know, you have rabbits and you have deer, and they're both competing for foliage on the ground. I don't know. they're both competing for some shared resource, okay? So we're going to let x of t and y of t be the population of each species. And the environment can only support a limited number of each species, right? It can support so many deer, it can support so many rabbits, and you know, there's a mixture, right? Maybe a lot of deer and a few rabbits, or a middle number of both, or a lot of rabbits and a few deer, right? But there's a limited number of resources. All right. Again, so let's just keep those carrying capacities, which I'll call K1 and K2, in the back of our mind. K1 is sort of the carrying capacity that has to do with species X, and K2 is the carrying capacity that has to do with species Y. And again, what we're going to do, let's just assume that the birth rate of species X is proportional to the current population. So we'll call that constant of proportionality R1, and the birth rate of species Y is proportional to the current population, so we'll call that constant of proportionality R2. And all right, now, as the populations of X and Y get big, the mortality rate of X increases, okay? So let's say that the death rate of X at time t, again, you have how many X's there are, and then this tells you what fraction of that population is dying at time t, okay? And we want the fraction of the population that's dying at time t. Let me erase this. Okay, to get bigger than R1 once there are too many X's and Y's. Okay, so what we'll do is we'll take R1. So again, we're looking at the fraction of the population that dies at time t. Okay, it's R1 times X plus alpha 1, 2y over K1. So what this is doing is saying that you have so many X's, alpha 1, 2y, this constant proportionality alpha 1, 2, that lets you treat Y's differently than X's, right? So maybe, you know, in terms of eating up resources, one rabbit is worth 3 deer or something like that. So you have this constant proportionality for the Y's, right? So once you have too many X's and too many Y's, in particular, once this ratio gets above K1, then the fraction of the X's that are dying at time t gets above R1, and so you have more deaths in the X's than you have births, okay? And then we'll do the exact same thing for the death rate of the Y's, right? You'll have the death rate of Y's at time t is going to be the current population times, now you have a fraction of the population that's dying at time t. That's right here. That fraction of the population needs to be related to R2 so that as you get too many X's and Y's living in your environment, the death rate of the Y's can get bigger than their birth rate. Okay? So again, what we'll do is we'll take Y plus a different constant proportionality, alpha 2, 1x. Okay? Once that gets above K2, then this fraction will be bigger than 1. So the fraction of Y's that are dying at time t will get bigger than R2, and you'll start losing Y's faster than you're gaining them through birth. All right? So we'll put this all together. The rate of change of population X is the birth rate of X minus the death rate of X, and the rate of change in population Y is the birth rate of Y minus the death rate of Y. And if you put that together, then you can get this equation right here, this system. But if you look in the book, if you just factor stuff out, you'll see the right-hand side of the equation written in this form, which is just fine. Again, this is called a competition model. All right. Okay, and again, for both the predator-prey model and for the competition model, you need to be able to find the equilibrium solutions, and you need to be able to tell me whether the equilibrium solutions are stable or unstable. Finally, I'd like you to understand these models well enough that if I change it up just a little bit and say, well, let's assume that the birth rate in one of the species is different, and I tell you how the death rate is different, then I'd like you to be able to come up with a different set of differential equations that represents those assumptions, okay? But again, if you've paid attention, you'll notice that, again, what we're always doing, it's the rate of change in the population is always just the birth rate minus the death rate. Birth rate minus death rate, and that's it, okay? So that's pretty much it. Those are the major models that we need to know for using systems of differential equations.